Welcome to lesson 3 on chemical changes. In this lesson we're going to be looking at displacement reactions. Make sure you've watched videos 1 and 2 before moving on to this content. To begin with, let's see if you can recall the reactivity series from last lesson, from most reactive to least reactive. You should have got your reactivity series like this. Check your answers now and see if you can remember this off by heart. So, to summarise, the first 4 metals reacted readily with water at room temperature. They gave off lots of hydrogen gas in the process. The next set of metals would react with steam, so still water but at a higher temperature, but it was difficult to compare their reactivities, so instead we reacted them with acid. Finally, copper, silver, gold and platinum. Well, copper and silver would react very slowly with acid, but so slow it was difficult to compare them to the rest. And gold and platinum didn't react with acid at all, being the least reactive of our metals. So today we're going to be looking at a type of reaction called displacement. And to understand this, I want you to imagine 2 people that have just met at a disco. We'll call this chap over here tin and this girl sulfate. And they've started dancing at the disco. But then all of a sudden, potassium enters the dance floor. And sulfate realises she'd much be rather dancing with potassium than with tin. This gives you the idea of what displacement is. So, we could summarise this with an equation. Tin sulfate plus potassium goes to make potassium sulfate plus tin. This is an example of a displacement reaction because a more reactive metal has displaced a less reactive metal from an aqueous solution of its salt. That final bit just means that these reactions take place in water. We can use the reactivity series to determine whether or not a displacement reaction will occur. Let's take this example here. Copper sulfate plus magnesium goes to make magnesium sulfate plus copper. We need to compare the reactivity of the incoming metal with the metal already paired up in a compound. So, we can see that copper is quite low on the reactivity series, meaning it has a low reactivity. Magnesium is higher on the reactivity series, so it's more reactive than copper. So, therefore, because this metal is more reactive than the metal already in the compound, displacement will occur. We can explain this using this type of sentence here. The reaction does occur because magnesium is more reactive than copper, so magnesium is able to displace copper. So in this example, the copper has been displaced. It's important to say that one metal is more reactive than the other and name both metals in that process. Don't just say it's higher on the reactivity series, so it happens. Say magnesium is more reactive than copper, so magnesium is able to displace copper. So you need to name those metals frequently and compare their reactivity explicitly. Don't just talk about being high or low on the reactivity series. Let's have a look at another example. In this example, someone said that copper sulfate can react with silver to make silver sulfate plus copper. Let's consider whether or not this reaction would occur. Here's copper on the reactivity series, but the incoming metal, silver, is actually lower down on the reactivity series. So silver is less reactive than copper. Therefore, this reaction will not occur, and that's because silver is less reactive than copper, so silver is unable to displace copper. So, I'm going to give you a whole bunch of reactions now, and it's your job to work out whether or not a displacement reaction will occur, and if it does or doesn't, you need to write a brief explanation of why. Here are your examples here, 1 to 6. Have a go at these questions, and then come back to check your answers. In the first reaction, someone said that copper chloride could react with iron to form iron chloride plus copper. We can see that the incoming metal, iron, is more reactive than copper, so yes, this reaction will occur. The metal that's been displaced is always the one that's on its own in the product, not paired up in a compound. So in this case, copper has been displaced because it's the less reactive metal that was displaced by the more reactive metal. So now let's give an explanation of why this occurs. Iron is more reactive than copper, so iron is able to displace copper. Example 2. Someone said that zinc can displace iron from iron sulfate. Let's have a look. Zinc is here on the reactivity series and iron is here. So zinc is more reactive than iron, so this reaction will occur. Which metal is displaced? Well, iron's no longer in a compound in the products, so it's been displaced as the less reactive of the pair. Let's give an explanation. Zinc is more reactive than iron, so zinc is able to displace iron. Next example. Someone said that iron sulfate can react with copper to form copper sulfate plus iron. Well, copper's here on the reactivity series, but iron's here. You'll notice that this incoming metal, copper, is actually less reactive than iron. So no, this reaction will not occur. So there isn't actually a metal that's been displaced in this case because it would have never got to those products in the first place. Let's explain why this reaction doesn't occur. Copper is less reactive than iron, so copper is unable to displace iron. Example 4. Someone said that lithium nitrate can react with calcium to form calcium nitrate plus lithium. Let's compare the reactivity of our incoming metal with the metal already bonded in a compound. Calcium is here on the reactivity series and lithium is here. This means that calcium is less reactive than lithium, so no, this reaction will not occur and neither metal has been displaced. We're going to say it doesn't occur because the calcium that's incoming is less reactive than lithium, so calcium is unable to displace lithium. For number 5, someone said that aluminium iodide can react with sodium to form sodium iodide plus aluminium. Let's compare the reactivities of those metals. The incoming metal, sodium, is more reactive than the metal already in the compound, aluminium. So yes, this reaction will occur. The metal that's displaced is always the one that's less reactive, so in this case, aluminium. Let's explain why it occurs. Sodium is more reactive than aluminium, so sodium is able to displace aluminium. Finally, which metal from the reactivity series shown here will displace all other metals and why? Well, the most reactive metal will be able to displace all others. So, potassium is the most reactive metal shown on our reactivity series, so is more reactive than all other metals, so is able to displace them all. Potassium isn't the most reactive metal of all the metals, but it's the most reactive metal that we look at GCSE. Our next goal is to be able to construct balanced symbol equations for displacement reactions. You've already practiced writing word equations for displacement reactions in the previous examples. Now what we want to do is take the names of these chemicals and write chemical formulae for them to make a symbol equation. For instance, you'd need to be able to work out that copper sulfate is CuSO4, magnesium is Mg, magnesium sulfate is MgSO4, and copper is Cu. By the end of this part of the tutorial, you should be able to construct equations like this yourself, but it's quite a challenging skill, so do bear with me. Things that have elemental names like copper and magnesium can simply be found on the periodic table. Copper is Cu, magnesium is Mg. I've written those into the formulae here. But you might notice that this sulfate part has been given the formula SO4, so therefore copper sulfate becomes CuSO4. How would you know how to do that? Well, there's a series of rules that you've got to learn. If the name contains nitrate, sulfate, carbonate, hydroxide, or ammonium, then you won't find this part of its chemical formula on the periodic table. Instead, you have to remember those parts of the formula off by heart. Nitrate is NO3, sulfate is SO4, carbonate is CO3, hydroxide is OH, and ammonium is NH4. You might also notice that some chemical formulae contain different ratios within them. For example, sodium sulfate, you will be forgiven for thinking that it's Na for sodium, SO4 for sulfate. But actually that's not true. Sodium sulfate has the formula Na2SO4. You can see here we've got 2 atoms of sodium for every 1 sulfate. Sulfate is the whole SO4 group. So if I've just got SO4 written like that, then I've got 1 sulfate. So 2 sodiums for every 1 sulfate. You might be thinking, why is SO4 one sulfate? Isn't it four? Well, no. Sulfate is a compound ion. In other words, it's a small collection of atoms that always exists as a group. That group contains one atom of sulfur and 4 atoms of oxygen, O. So this is actually one sulfate because it's one of that whole chunk. Another example would be magnesium nitrate. You might be thinking it's just MgNO3, but that's not the case. There's a ratio within this formula. The formula actually turns out to be MgNO3 within brackets 2. This means that we've got one magnesium atom for every 2 nitrates. Nitrate being the NO3 group, and it being put in brackets like this with a 2 afterwards to state that we have 2 of the nitrate group. We'll look a little bit more at how to use these brackets in future examples. But to begin with, let's just go back to basics and see if we can name some compounds. So, I've given you a range of compounds here, and we're going to try and name them, but I'm going to give you some handy rules to help you name them. To begin with, use the periodic table to try and name elements if you can. Always name the metal first. And then finally, if the formula contains SO4, then it's something sulfate. NO3, then it's something nitrate. CO3, then it's something carbonate. OH, and it's something hydroxide. And these are the special ones, the compound ions, which can't be found on the periodic table. So let's start with A. It's got Mg for magnesium and Cl for chlorine, but when chlorine's in a compound, it becomes chloride. So we've got magnesium chloride. B. Li is lithium and Br is bromine, so this compound will be lithium bromide. The next one, we've got Ca for calcium, and we've got an SO4 group, and you should remember that that makes it something sulfate, calcium sulfate. The next one, we've got Mg for magnesium, and NO3. That should be easy to spot as a nitrate group. So in this case, we've got magnesium nitrate. In the next one, we've got Na for sodium, and CO3. Whenever you see CO3, you should associate it with carbonate. And then finally, we've got Ca for calcium and OH. Whenever you see OH, you should call it a hydroxide. Now, let's have a look at the ratios within these formulae. In magnesium chloride, you've got 1 magnesium for every 2 chlorides. In lithium bromide, you've got 1 lithium for every 1 bromide. In calcium sulfate, you've got 1 calcium for every 1 sulfate. SO4 being a whole sulfate group, so you've only actually got 1 of them there. Magnesium nitrate, you've got 1 magnesium, and you see the NO3 for the nitrate group, you've got 1 of them there, but because it's in brackets, you've actually got 2 of the whole nitrate group. So this one gives us 1 magnesium for every 2 nitrates. In sodium carbonate, you can see that we've got 2 sodiums for every 1 carbonate, where the CO3 group is a whole carbonate. In calcium hydroxide, you've got 1 calcium for every 2 hydroxides, because that compound ion there has been put in brackets. Now let's try to work out where these ratios actually come from. The ratios within these compounds stems from the fact that we're looking at ionic compounds. And before we move further into this, we need to recap how we find the charge of an ion within an ionic compound. To begin with, let's have a look at the metals in this section here of the periodic table. Remember that metals will always form positively charged ions because they lose their negative electrons whenever they've reacted to form an ionic compound. If you're in group 1 of the periodic table, then you lose 1 electron, like these here, so you only form 1 plus ions. So lithium would be Li+, sodium would be Na+, and potassium would be K+. If you're in group 2 of the periodic table, then you lose 2 electrons when you react, so you form 2 plus ions. Magnesium would be Mg2+, and calcium would be Ca2+. If you're in group 3 of the periodic table, like aluminium over here, then you would lose 3 electrons when you react, so you would be Al3+. The metals in the central block of the periodic table are known as the transition metals, and you might notice that there's no group numbers above them here. That's because they can form ions of different charges. In exam questions, the charge of a transition metal will always be given as a Roman numeral. So, copper I means copper 1, so that's Cu+, because it forms a 1+ ion. Copper 2 would be copper 2+. Iron 2 would be iron 2+. Iron 3 would be iron 3+, and zinc 2 would be zinc 2+. Now let's have a look at the non-metals on the periodic table. Non-metals always form negatively charged ions, and all you need to do is find the group number that the non-metal is in and see how many it takes to count up to 8, because they've got to gain electrons to get a full outer shell. So if you're in group 7, you've only got to go up 1 in order to get to 8. So anything in group 7 gains 1 electron, so forms a 1- ion. For example, fluoride F-, chloride Cl-, bromide Br-, and iodide I-. If you were in group 6, then in order to get up to 8, you've got to gain 2 electrons. So oxygen would need to gain 2, so it would be O2-, and sulfur, for example, would also need to gain 2, so it would be S2-. Now let's get to those compound ions that we talked about in the past examples. The compound ions, you need to remember their charges off by heart. It's very important that you remember these. Nitrate is NO3 with a 1- charge. That's 1- because there's not a number in front of the minus. Sulfate is SO4 with a 2- charge. Carbonate is CO3 with a 2- charge. Hydroxide is OH with a 1- charge. We're going to skip ammonium for now. Now let's look at how we can use the charges of those ions to construct the chemical formulae. Let's focus on this first example that we looked at, magnesium chloride, which had 1 magnesium for every 2 chlorides. Let's find magnesium on the periodic table. Here it is. It's in group 2 of the periodic table, so it will form an Mg2+ ion. Now let's look for chlorine on the periodic table. It's over here. Chlorine's a non-metal in group 7, so it gains 1 electron and it will become Cl-. If we tried to pair up these ions like this, you've got a 2+ charge and a 1- charge, so the charges wouldn't cancel out. You'd end up with MgCl, but it would have an overall positive charge because you've got 2 pluses but only 1-. We need to write the formula in a way that gives it no overall charge, so this is wrong. Instead, we would need 2 chlorines, each with a 1- charge, for every 1 magnesium to cancel out the charge fully. That's what gives us MgCl2, because we have 2 negatives and 2 positives. In our next example, we'll look at lithium bromide. Here's lithium, a group 1 metal, so it forms a 1+ ion. Bromine is in group 7, so it's a non-metal and it will gain 1 electron to get a full outer shell of 8. So, bromine forms Br-. We can see here that the charges of each ion are equal and opposite, so these can be paired together in a 1-to-1 ratio, just as they were in the formula. Now let's have a look at calcium sulfate. Calcium is a group 2 metal with a 2+ charge, so calcium will be Ca2+. Sulfate, however, was one of our compound ions which could not be found on the periodic table. We had to remember this one off by heart. So remember that sulfate was SO4 with a 2- charge, nitrate was NO3 with a 1- charge, carbonate was CO3 with a 2- charge, and hydroxide was OH with a 1- charge. So the other ion in calcium sulfate is SO4 2-. We can see here we've got 2 pluses and 2 minuses, so these two can be paired together in a 1-to-1 ratio, CaSO4. That's 1 calcium for every 1 sulfate, where sulfate is SO4. Next, let's look at magnesium nitrate. Magnesium is a group 2 metal which can be found on the periodic table, so it's Mg2+. Nitrate is a compound ion, so therefore it cannot be found on the periodic table in its whole NO3 form. Nitrate was NO3 with a 1- charge, so nitrate is NO3-. You can see here we've got Mg2+, but it's important to note that this NO3 group only has a 1- charge. It has one nitrogen atom, 3 oxygen atoms, with a 1- charge overall. If I paired these two together, I would end up with MgNO3. However, because I've only got 2 pluses and 1-, overall the positives of the magnesium would almost shine through. Imagine it like that. So this thing would have an overall positive charge. And remember that we need to write the formula so it has no overall charge. So therefore we're going to need 2 of this nitrate group, each with a 1- charge, for every 1 of the magnesium with a 2+ charge. So we end up with the formula MgNO3 2. By putting the NO3 in brackets and then putting a 2 on the outside, it's like saying I have 2 nitrates. And this is a rule. If you ever have more than one of these compound ions to balance for charge, then you have to put it in brackets. Now let's look at sodium carbonate, Na2CO3, which has 2 sodiums for every 1 carbonate. Sodium can be found in group 1 of our periodic table, so it forms Na+. Carbonate is a compound ion, which is 2- in charge overall. So we write CO3 for carbonate with the 2- charge. You can see here I've only got 1 positive for every 2 negatives. So therefore, if I was to write the formula like this, NaCO3, then there'd be more negatives coming from the carbonate than positives coming from the sodium. So it'd have a 1- charge overall. This is wrong because we need to balance for charge. So therefore, I need 2 positives to cancel out the 2 negatives of the carbonate, so I'd end up with Na2CO3. Now let's have a look at calcium hydroxide, which has 1 calcium for every 2 hydroxides. Calcium is a group 2 metal found on the periodic table, so it forms a Ca2+ ion. Hydroxide is one of our compound ions that has a 1- charge, so it's OH-. You can see here I've got 2 positives but only 1 negative, so if I was to put these together in a 1-to-1 ratio, I'd end up with a 1+ charge overall, which is wrong because we need to balance for charge. To cancel out the 2 positives of the calcium ion, I'm going to need 2 of the hydroxide, and because it's a compound ion, I'm going to put it in brackets. So I would write CaOH2. Now let's look at copper nitrate, CuNO3 This compound has 1 copper for every 2 of the nitrate. Now, copper is a transition metal, so we can't find its group number on the periodic table because the transition metals aren't given group numbers. But you can imagine this little 2 here written after the copper to be basically the same as its group number. So that copper 2 there is actually copper 2+. Nitrate is a compound ion, so it's NO3 with a 1- charge. So this whole NO3 group only has a 1- charge. We've got 2 pluses and 1-. If we paired them together 1-to-1, then there'd be more positives than negatives, so this would end up with a positive charge, which is wrong. So instead we need 2 nitrates, each with a 1- charge, to cancel out the 2 positives of the copper ion. So we'd get CuNO3 2. Let's have a look at a really hard example now. Iron 3 sulfate. Iron is a transition metal, so it's not given a group number. As you can see here, there is no group number in the row above it. But we're given its charge here because it's iron 3, so we know that it's Fe3+. Sulfate is one of our compound ions. It has a 2- charge. Now if I paired these two together 1-to-1, I'd end up with an overall positive charge because I have 3 pluses and 2 minuses. This is wrong because we need to balance for charge. Instead, we need to find a number that both 3 and 2 fit into, 6. In order to get 6 pluses, I'd need to multiply the iron by 2. And in order to get 6 minuses, I'd need to multiply the whole sulfate group by 3. So we end up with the formula Fe2, meaning 2 ions each with a 3+ charge to give 6+, and 3 sulfates, each with a 2- charge to give 6- overall. Again, I've written the sulfate in brackets because I have more than one of a compound ion. So, now what we need to do is work with these formulae. So your first task is to try to name these compounds. Then I want you to try to construct formulae, as I just did, for these compounds here. Pause the video and then come back to check your answers. This has Mg for magnesium and OH for hydroxide, so it's magnesium hydroxide. Here we've got sodium, and I've seen an SO4 group, so it must be sodium sulfate. Here I've got aluminium and Cl. It's got to be aluminium chloride. Here I've got Ca and NO3 for a nitrate group, so this becomes calcium nitrate. Next we've got to construct formulae for the following compounds. Lithium sulfate. Well, lithium is a group 1 metal, so it's Li+, and sulfate is a compound ion with a 2- charge. So we've got Li+ and SO4 2-, but in order to balance for charge, I need 2 lithiums for every 1 sulfate, so I get Li2SO4. Magnesium nitrate. Magnesium is a group 2 metal, so it forms a 2+ charge. And nitrate is one of the compound ions that we need to remember. It's NO3 with a 1- charge. Notice how there's no number written directly in front of that minus there. The 3 is referring to the oxygen, not the charge. I've got 2 pluses and 1 minus. So I need to have 2 of the nitrate for every 1 of the magnesium in order to balance for charge. And because nitrate is a compound ion, I need to bracket it if I have more than 1 of it. So you should have got MgNO3 2. Calcium carbonate. Calcium is a group 2 metal with a 2+ charge. Carbonate is a compound ion with a 2- charge, CO3 2-. We can see the charges are equal and opposite, 2 pluses and 2 minuses, so these two can go together in a 1-to-1 ratio to form CaCO3. There's some more practice now on that skill to really make you master it, so please pause the video and have a go at attempting these, then come back to check your answers. Magnesium is a group 2 metal, so it forms an Mg2+ ion. Fluorine is a group 7 non-metal, so it gains 1 electron and forms F-. We can see that we've got 2 pluses but only 1 minus, so I'm going to need 2 of the fluoride for every 1 of the magnesium. This will give me MgF2. Sodium hydroxide. Sodium is group 1, so forms Na+. Hydroxide is a compound ion, we should know it as OH-. We can see here the charges are equal and opposite, so they pair together in a 1-to-1 ratio to form NaOH. Aluminium nitrate next. Aluminium is a group 3 metal, so forms an Al3+ charged ion. Nitrate is a compound ion which we need to remember. It's NO3 with a 1- charge. Here I've got 3 pluses and only 1 minus, so I need 3 minuses overall, so I need to multiply this nitrate group by 3. So I'll put it in brackets, multiplying it by 3. Al, NO3, 3. That's 1 aluminium for every 3 nitrates. Copper 2 chloride next. We can't find copper on the periodic table as a group number, so we just need to know that it's copper 2+ from its Roman numerals here. Chlorine is in group 7, a non-metal, so it's Cl-. We've got 2 pluses and only 1 minus, so we need to multiply the chlorine by 2 in order to write its formula. So we get CuCl2. Iron 2 would be Fe2+. Nitrate is NO3 with a 1- charge. Here I've got 2 pluses and only 1 minus, so I need to multiply the nitrate group by 2 in order to balance. Finally, iron 3 bromide. Iron 3 is Fe3+, bromine is in group 7, so it gains 1 electron to form a Br- ion. I've got 3 pluses and only 1 minus, so this will be FeBr3 in order to get 3 minuses overall to cancel out the 3 pluses. You might be wondering why, when I multiplied this fluorine up here by 2, I didn't put it in brackets, again for the chlorine here, and again for the bromine here. Well, that's because they're not one of the compound ions. You only need to bracket up sulfate, nitrate, carbonate, hydroxide if you have more than one of them. So it's only compound ions which we put in brackets when we have multiples of them. So now what I want you to do is try to write the formula in the gap to balance these symbol equations for displacement. So all you need to do is look at the name above in the word equation and work out its formula, and then plug that formula into the gap. So lithium nitrate should have got you LiNO3. Don't worry too much about the state symbols if you didn't get them, but this one was aqueous because it's occurring in aqueous solution like most displacement reactions do. For this next one we had to fill in 2 gaps. Magnesium nitrate. Magnesium is 2+ charged, whereas nitrate is only 1- charged. So we need 2 nitrates for every 1 magnesium. So we should have got MgNO3, 2. Sodium nitrate. Well, sodium is 1 plus charged and nitrate is 1 minus charged, so they can go together in a 1-to-1 ratio. So we should have got NaNO3 for sodium nitrate here. Next up, copper 2 sulfate. Copper 2 means it's 2 plus charged, and the sulfate is always 2 minus charged, so those two work together in a 1-to-1 ratio, 1 copper for every 1 sulfate. Magnesium sulfate is much the same, because magnesium is a 2 plus ion and sulfate is a 2 minus ion, so we get MgSO4. Some more here for practice, so please pause the video, give them a go, and then come back for your answers. Here we've got copper 2 chloride. Copper 2 is 2 plus charged, and chloride is 1 minus charged, so we should have got CuCl2 for the copper chloride. In potassium chloride, potassium is 1 plus charged, whereas chlorine is 1 minus charged, so they pair together in a 1-to-1 ratio, so potassium chloride is KCl. Next up we've got iron 3 nitrate. Iron is a 3 plus charge, in this case because it's iron 3, whereas nitrate is only a 1 minus charge. So we're looking at FeNO3 3, meaning we've got 1 iron for every 3 nitrates. Magnesium nitrate is different. Magnesium has a 2 plus charge, whereas nitrate has a 1 minus charge, which means we need 2 nitrates for every 1 magnesium. So we should have got MgNO3 2, showing 2 nitrates for every 1 magnesium. Finally, we had to fill in every gap in this equation. Iron 2 sulfate first. Iron 2 is Fe2+, sulfate is 2-, so these two pair together in a 1-to-1 ratio. 1 iron for every 1 sulfate, SO4. Zinc is just Zn. Let's have a look at zinc 2 sulfate. Zinc 2 is zinc 2+, sulfate is SO4 2-, so they pair together in a 1-to-1 ratio, so we get ZnSO4. And iron is just Fe. Right then guys, thank you very much for watching that video. The second part of it was particularly challenging. You will get opportunities when we're back at school to go over that quite a lot of times again, so don't worry too much if you found that second half challenging. As long as you've got the idea of the displacement word equations and explaining why they do or do not occur, then that's the main objective from today's lesson. Just wanted to stretch you a little bit further to get you working with formulae so we don't forget all of that while we're off. I hope you enjoyed the video, and we'll see you for the next one where we're looking at reduction using carbon. See you then. Thank you.